Now we will be talking about multi-dimensional arrays, right? Right. So, multi-dimensional arrays in programming is actually not a very common format or a common used topic, right? So multi-dimensional arrays, what is multi-dimensional arrays, right? It's actually an extension of the 1 and 2D dimensional arrays where data is organized across multiple dimensions. These arrays can represent complex data structures, making them useful for a variety of applications, right? So you can use them, like these arrays are used in scientific programming, graphics, data processing. So the structure and definition is same. While one-dimensional arrays represent list and two-dimensional arrays represent tables, multi-dimensional arrays can go beyond that and extend this concept to 3 or more dimensions. Each dimension adds a level of complexity, allowing the array to store data in a structured format that can represent, for example, cubes or hypercubes in a higher dimension. Right? So, three-dimensional array can be visualized as a collection of 2D arrays stacked on top of each other. For instance, consider a 3 into 3 into 3 array, right? It will be a little bit difficult to even visualize that. I will type it out for you, right? right? So this is a 3D array, right? The element 14 is accessed using this thing, R1 1 1, right? So it represents the second block, second row, second column, right? Then declaring and initializing a multi-dimensional array. Arrays are declared by specifying the size of each dimension. For example, in a language like C++, a 3D array of integers with 4 into 3 into 2 might be declared as int r432. Initialization. Multidimensional arrays can be initialized by nesting list or arrays within each other to match the example, to match the number of dimensions like this, like the one I've told you. And you can also create a 2 into 2 into 2 array where each layer contains a 2 into 2 matrix, right? So it's a different concept. Let me just create a particular array to show you how it's done. Right. So this creates a 2 into 2 into array where each layer contains a 2 into 2 matrix. Right. So accessing elements, multi-dimensional arrays, multi-index access is different. To access each element in a multi-dimensional array is accessed using a corresponding number of indexes. For example, in a 4D array, AR3 3, 2, 1 and then one more 4 will be here. You can access the element in the fourth dimension, within the first element of the third dimension, within the second element of the second dimension, within the third element of the first dimension. Right. It's a little bit complex, but you will understand it once you start doing it. Right. Once you start doing it, you will understand it clearly. So efficiency of accessing an element in a multi-dimensional array is sufficient over one time. Complexity, as long as you know the indexes, right? We already know this, right? The complexity of indexing increases with each dimension, each added dimension, making the code harder to read and maintain. Common operations is like iterating over a multi-dimensional array requires nested loops, one for each dimension. For a 3D array, for instance, you need 3 nested loops, right? The kind of iteration is useful for processing or analyzing data in multidimensional arrays, right? Searching in multidimensional arrays is similar to one-dimensional arrays but involves more nested loops. You can check each dimension until the desired element is found. So it's a bit complex than one-dimensional, two-dimensional, but the structure is also complex, so that is kind of expected, right? Then we have matrix and tensor operations in scientific computing. Multidimensional arrays are often used to represent matrices 2D and tensors 3D and beyond. Operations like tensor multiplication, slicing, and reshaping are common in fields like machine learning and physics. Then we have memory management, memory layout. In a row major language, the elements of a multidimensional array are stored in contiguous memory. For a 3D array, all elements are stored in a 2D sub-array. Slice are stored together, followed by the next slice. Understanding the memory layout is crucial for optimizing performance, particularly in large data sets, right? Then we have memory usage. Multidimensional arrays can consume significant memory, especially as the number of dimensions increases. For example, a 4D array with dimensions for 10 into 10 into 10 into 10 into 10 would require memory for 10,000 elements actually. So each element's memory requirement depends on its data type, so it's important to ensure that enough memory is available in dynamic for this. And we also have dynamic allocation. In some languages, multidimensional arrays can be dynamically allocated, allowing flexibility in managing memory. However, keep in mind that dynamic allocation also requires carefully memory management to avoid memory leaks and ensure proper deallocation is done when the array is no longer needed, right? So advantages of multidimensional arrays, right? Multidimensional arrays are ideal for representing complex data structures like 3D models, simulation grids, multidimensional matrices, making them useful in scientific computing, graphics, and engineering. We have efficient data access. Despite their complexity, multidimensional arrays still allow for efficient data access when the nature of the data fits naturally into a grid-like format. And this is especially important in performance-critical applications. That is the reason arrays are used rightly. And mathematical computation in fields like linear algebra, physics, machine learning, multidimensional arrays, tensors are fundamental for performing mathematical computations on a large data set. As always, there are some limitations of arrays, multidimensional arrays, as one-dimensional, two-dimensional, multi-dimensional, all of them have some limitations. So the limitation is complexity. As the number of dimensions increases, the complexity of managing understanding the array also increases. So this can make the code harder to maintain, more prone to errors. Multidimensional arrays can consume a large amount of memory, particularly in higher dimensional spaces. Managing this memory effectively is crucial, and especially in a resource-constrained environment, right? In some cases, the performance of operations on multidimensional arrays can degrade due to the complexity of the data structure. Optimizing memory access patterns and minimizing cache misses becomes more challenging as the number of dimension constantly increases, right? So we have some real world applications of multidimensional arrays, mostly in scientific simulations, but that's something which is kind of expected with these kind of complex data structures, right? For complex things we need complex data structures. So first is scientific simulations. Multidimensional arrays are often used in simulations of physical systems such as fluid dynamics, weather models, molecular simulations, or something where data must be represented in a 3D or a higher dimensional space, right? It's used in image and video processing. In graphics and video processing, multidimensional arrays are used to represent image data 2D and video frames 3D with pixels or frame rate represented by an element in the array. It's also used widely in machine learning. In machine learning, multidimensional arrays, often called tensors, are used to represent data and perform operations like tensor multiplication, convolution, and backpropagation in neural networks, right? Data analytics. Multidimensional arrays are used in data analytics to represent complex data sets such as time series data, multidimensional cubes, and more. Some example cases of these arrays would be: consider weather simulation program that needs to model temperature, humidity, and pressure across a 3D grid of geographic locations over time. A 4D array can be used to store this data, where the 4 dimensions represent time, latitude, longitude, altitude respectively. So this allows the program to efficiently and effectively store and access the data needed for complex simulations. Always keep in mind the best practices. Keep dimensions manageable. If possible, keep the number of dimensions in your array to a minimum. High dimensional arrays can become difficult to manage and understand. Use appropriate data types. Choose the smallest data type that meets your needs to minimize memory usage, especially when working with large multidimensional arrays which are complex to understand and create and maintain, right? So yeah, this and always optimize memory access patterns in a performance critical application. Pay attention to how your program accesses elements in multidimensional arrays. Optimizing for cache locality, accessing contiguous memory locations can significantly improve performance, right? Consider some alternatives. In some cases, other data structures like linked list, trees, or hash tables, which might be more appropriate than a high dimensional array, particularly if the data is sparse or irregularly shaped, right? So multidimensional arrays are a powerful and versatile data structure that can represent complex data in a structured format. They are essential in fields like scientific computing, graphics, machine learning, where data is naturally multidimensional. Understanding how to declare, initialize, access, manage memory for multidimensional arrays, it's crucial for effectively using them in your programs. While they can offer great flexibility and efficiency, they also come with challenges in terms of complexity, memory management,